Plastics are called plastics because of how they behave, not how they look. Heat a plastic bottle and it softens, flows, and can be reshaped. Cool it down and it keeps that new shape. Glass shatters. Metals need extreme heat, but plastics sit in this sweet spot where shaping is easy and stable. That behavior comes directly from chemistry. At the molecular level, plastics are made of polymers. A polymer is one enormous molecule formed by linking many small molecules, called monomers, into long chains. Take polyethylene as a simple example. Ethylene molecules, CH2 equals CH2, link together into chains thousands or even millions of units long, forming a backbone of repeating CH2-CH2 units. That sheer size already makes polymers very different from most substances. Inside each chain, the atoms are held together by strong covalent bonds. These bonds form the permanent skeleton of the molecule, which is why plastics are durable and don't just fall apart. But different chains are usually not fully bonded to each other. Instead, they attract through much weaker forces, like van der Waals forces, dipole interactions, or hydrogen bonds, depending on the polymer. This split between strong bonds within chains and weaker forces between chains is the key to plastic behavior. When you heat a plastic, you are not breaking the covalent backbone, you are weakening the attractions between chains. As those interactions loosen, chains can slide past one another. That motion allows the material to flow under pressure into a mold or through an extruder. When it cools, those interactions strengthen again, locking the chains in place and freezing the shape. Chain length matters too. Polymer chains are so long that they become tangled, like cooked spaghetti in a bowl. These entanglements resist motion, making plastics solid at room temperature, even without permanent bonds between chains. Under heat, the tangles loosen just enough to allow slow, viscous flow instead of a watery liquid. That is why molten plastic pours thickly, not like melted ice. The exact structure of the chains controls how a plastic feels and behaves. Linear chains pack closely and often form stiffer materials. Branched chains pack poorly, leading to softer, more flexible plastics. If chains are chemically cross-linked, forming a three-dimensional network, the material becomes rigid and will not melt again. Those are thermosets. Plastics that soften and remelt are thermoplastics, where chains remain separate. Side groups attached to the backbone also matter. A small side group, like a hydrogen atom, allows easy rotation and flexibility. A bulky group, like a phenyl ring in polystyrene, restricts motion and makes the plastic hard and glassy. Polar side groups increase attraction between chains, raising stiffness and softening temperature. Tiny changes in molecular structure produce large changes in material properties. Most plastics are neither fully ordered nor fully disordered. They contain crystalline regions, where chains pack neatly, and amorphous regions, where chains are tangled and random. This mix, called semi-crystallinity, explains why plastics can be tough but not brittle. Crystalline regions provide strength, while amorphous regions allow deformation. Temperature controls how these regions move. Below the glass transition temperature, amorphous regions are frozen and the plastic feels hard or brittle. Above it, chain segments can move and the plastic becomes rubbery or flexible. Some plastics also have a melting temperature, where crystalline regions break apart and the material flows more freely. All of this explains why plastics are so easy to engineer. Chemists adjust chain length, branching, side groups, crystallinity, and additives to dial in specific properties. The result is not one material called plastic, but an entire family, ranging from soft films to rigid housings to tough fibers. So, what makes plastics plastics is not their origin or their appearance. It is their molecular architecture: extremely long chains, held together strongly along their length, weakly between neighbors, able to move with temperature, tangle with one another, and lock into place when cooled. That combination is what turns simple molecules into moldable, durable materials that shape the modern world.